we will talk about basics of a probability. You might have heard this term a lot, right? Probability, or you might have heard this word like a chance. All right. The single most important objective of this section, okay, is to learn how to interpret probability value. Usually, the probability value will be expressed as a decimal, 0 point something, and or you can use fractions. Either way, you can do that. And all the probabilities should be, I call that less than or equal to 1, greater than or equal to 0, which means 100%, literally that's 1, or 0%. That's the two boundaries. That's the upper boundary and the lower boundary of the interval for any probability we're going to talk about. Someone keeps saying that I am 200% sure, this is okay. You can just tell him that no, you don't know that. You don't really need 200%, 100%. It's already like sure, okay? It's just so sure. So 100% of a probability, or some events probability is 100%. That means guarantee that is going to occur. If the chance is 0 or probability is 0 or 0%, that means it will never ever happens. Okay, and then there are a couple of concepts. The first one is event. Okay, event is it's a collection of results or outcomes of a procedure. You do something, you observe, and you find some outcome, and we call that event. And the next one we call that a simple event. Okay, simple event, that is an outcome or an event that cannot be further broken down into simpler components. I'm going to give you the example. You can see what I'm saying here. And the other concept is called a sample space. Sample space for procedure consists of all the possible simple events. That is, the sample space consists of all outcomes that cannot be broken down any further. Okay, let me give you a quick example. When we talk about the newborn baby, or we just talk about one birth, okay, for this procedure, and what are the possible outcomes or the event? It could be a boy. It could be a girl, right? All right. So this is an event. This is an event. All right. And this, if you put them together, we call this sample space, because we cannot break down. We cannot go any further and just either boy or a girl. So that's the for the procedure, just one of a one birth. What about a two? Two births. I can show you how to use the little tree to show that for the first baby, it could be either boy. Let me just use a little b as a boy and a little girl, little g as a girl. So the first could be either boy or a girl. And then for the second baby, it could be either boy or girl. It has nothing to do with the gender of the first one. So it could be either boy or a girl. All right. Now, what is the sample space? The sample space will be boy, 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 girl, girl, boy, and a girl, girl. Did you see that? You have four simple events in the sample space if the procedure is two births. Okay. If I'm saying at least one boy, so that could be this one, could be this one, could be this one, right? At least one boy. This contains these three simple events. Understand? So, all right, if you're interested, you can go ahead, you can list what happened to three births. That could be boy, girl, boy, girl, boy, girl. And then the third baby could also be boy, girl, boy, girl, boy, girl, boy, girl. So it seems like you're going to have 8 simple events in the sample space of the procedure of 3 births. And of course, you can just go ahead and list them. You can just list, okay, B, 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 and so on. So there's going to be 8 of them. All right, so this is the first concepts we learn, events, simple events, and the sample space. All right, now we always use the P to show probability, and we use A, we use B, we use C, or those to show the events. It might be simple event, it might not be. So P of A, we're gonna say this shows the probability of event A occurring. So this is the probability that A happens. Okay, so this is the notation that we're going to use, and we know that a P of any event got to be between 0 and 1. What about 0.5? What happened when PA equals 0.5? What does that mean? That means the chance that this event A occurring will be 50%, isn't it? So that's like a half chance. You might have half chance that this happens, or half of the chance it won't happen. We can also call this likelihood. So the possible values of probabilities and the more familiar and common expressions of likelihood. So this is a very interesting number. It's a 50-50 chance, right? So this means a sure, highly, here it goes highly likely, and it goes to 100% sure, and certain for 0, which is impossible. So you know the how do you call that, the interval of the probability. All right, so that's the first important concepts. And the second part, we talk about the 3 common approaches to finding the probability of events. There are 3 ways to do it. 3 ways. Okay. The first one, relative frequency. All right, the relative frequency, which means you're going to repeat the procedure many times, and then you're going to count how many times you repeat the whole procedure and how many times this event A occurs. And then you're going to use the number of times A occurred divided by the number of times the procedure was repeated to get the probability of A. So the probability of A is the total number of a procedure and the number of A. So that's a relative frequency. If you remember that we did earlier, when we get the frequency table, then we can just go ahead and figure out the relative frequency table, right? All right, and so we want to see this, and this is the first one. Let me give you one example. I saw some statistic before. It says in Washington D.C. area, in summertime, like in August, if there are 3 consecutive sunny days, sunny, okay, and then for the 4th day, there's 85% of the chance it's going to rain, and 15% of the chance no rain. Okay, so this is, how do you get this 85%? You might wonder. And how do you get this 85 and 15%? All right, now they went through the past, for example, 10 years. So look at all the August data and to see how many days that we have 3 consecutive sunny days. All right, and then so that's how many days? How many days that already have 3S, okay? And then go ahead and you look at the 4th day, okay, after you have that, and look at the day after that. How many of them comes with the rain? So the number of days rain. This method you're using, you're getting the relative frequency of that, and this is the method we're using called using relative. We're going to use the relative frequency as the approach to get to the approach to for the probability. That's the first one, and we use this a lot, right? And the second method is called a classical approach. Classical approach, which means if this procedure has n different simple events and that are equal likely, that's a key word, equal likely, equally likely. All right, equally likely, which means every single simple event in the sample space has exactly the same chance to occur. For example, if you flip a fair coin, if you flip a coin and then you look at it when the coin lands, and then you're going to look at the face up, it could be either head or tail, right? So we just assume that they are equally likely occurred, so the probability of a head equals 1/2 or 50% or 0.5. You can say either one. And the same thing, probability of a tail is the same thing. Okay, so we have to assume that they are equally likely. The other very frequently used example is the die. 1, 2, 3, and there are 6 faces, and each face has dots on it, and there are 6 faces, so you can, if you count the dots, has 1, 2, 3, 4, 5, 6, then the probability, if you just throw it and then look at the face up to count how many, you're going to count how many dots there. What is the probability that you're going to get a 1? Since there are 6 faces altogether, and that's just one of them, so that would be 1 out of 6. All right, so this is the, we call this as a classical method or classical approach to get the probability. The third method, it's called subjective probability. What does that mean? And that means we use the knowledge of the relevant circumstances to get it. So we can just assume, or you just, based on your experience, you just tell me, okay, just tell me what is the chance. Because you probably, based on your perception, you think, oh, there's like it looks like we have more girls at a school, so maybe like a 55%. So you can just use that number sometimes when we do the calculation. That comes from your thinking or your call this a subjective probability. Okay. And also sometimes, other than this 3 method, sometimes none of the these 3 approaches can be used, and then we can use a simulation. And that's the last one. I didn't want to talk too much about this, but this is also people can use. If you have a computer, you can write a little program, you can use that. Because you can just, a simulation of a procedure is a process that behaves in the same ways as the procedure itself, so that similar results are produced. Probability can sometimes be found by using a simulation. You probably have heard this, because if there's no way, you cannot use the relative frequency, it doesn't exist, and it's not frequently equally likely occurred simple events, you cannot use the classical approach. And also you have no experience at all, so there's no subjective probability. Well, there's another option. You can use the simulation method. Okay. All right, now we are going to say, we're going to learn something called a law of large numbers. What is the law of large numbers? It just says, as the procedure is repeated again and again, the relative frequency probability of an event tends to approach the actual probability. So that's when you do the simulation. If you have the, for example, if you have the computer program to repeat some experiment, then you really have to do that many times. You cannot just do once, twice, or even maybe 5 times. So you have to do like a large number of times to get that. We have to be very careful when you use this, because this law of large numbers applies to behavior over a large number of trials, and it doesn't apply to any one individual outcome. You just do the experiment once and you get the outcome. You cannot rely on that. You have to do this many times. And the other thing we get to know is, if we know nothing about the likelihood of different possible outcomes, we could not assume that they are equally likely, right? The actual probability depends on factors such as the amount of preparation and the difficulty of the test. It might depend on several things. I'll give you a quick example. I think you might have heard this. I just think it's very interesting. There's a game, okay? So there are 3 doors. Let me call this as ABC. Okay. Let's see, there are 2 lions. There are 2 lions and $1 million. I just made this up. Behind that, I don't know which one is which. Okay, could be A, could be B, could be C, could be lion, $1 million, could be $1 million, lion, things like that. But all the doors are closed, so you don't open that, you don't see it. I won't tell you what is that. All right, now you come to play the game. I ask you to randomly select one. I just choose one which you believe that have $1 million behind it. Okay, so you pick one. Let's say you pick the A. Now the question is, for B and C, no matter what you choose, no matter what's behind the door you choose, I will tell you one of the rest 2 doors, one of them has a lion. So for example, I tell you C has a lion, so don't worry about that. Now, the real question is, should you switch? Should you switch to B, or you should stay with A? A lot of people think, okay, when I choose A, the chance of winning $1 million is 1/3. And then once you tell me that a C has a lion behind, I don't want to see lion, because the lion might just eat me alive. So I don't want to see lion. So do I need to switch to B? If I know there's a lion there, does that change the probability of this $1 million behind A and B? Becomes a 50-50? So either switch, after you know the information, you're going to switch, TCH, switch or not switch? That's a question. All right, now it is interesting. You can do some calculation and someone don't believe the answer. Guess what? You can do simulation. You can repeat this again and again and again, and then you figure out, oh, is that better to switch or is better not to switch? So I can just leave that as an interesting question for you guys. All right, now we learned some basic concepts, and we learned 3 different ways, even the 4th way to get the probability, and then we're going to do little exercise, and we're going to figure out this probability. All right, now the first one. The first one is airplane. In recent years, there were about 39 million commercial flights. Commercial airline flights, and 16 of them crashed. It's bad news. And I would ask you, what is the probability to find a commercial airliner will crash on any given flight? So the probability of a crash will be relative frequency, okay? So relative to a total of 39 million, there are 16 of them crashed. So that's how you do it. That's we're using the relative frequency to do it. And if you use your calculator, you're gonna find the answer is 0.0000041. It's really, really small, right? Or you change that into percentage, you move the decimal to the right twice, it's going to be 0.0000041%. It's a tiny little chance, which is a good thing, okay? It's not a zero. It's really close to zero, but it's not zero. So you're going to say, and it might be safer than you take a ride with a car, right? So that's the first example. Let me give you another example here. You ask people, okay, you do little research and then you ask people about a question. So it's like in 2002 survey, okay, and how many people you asked? You ask people, do you use internet? Think about this is like more than 20 years ago, a long time ago, right? Okay, so there's 1782 people, and they answered yes. They said yes, I use internet. And the others, we have 220 people. Their answer is no. Now the question: what is the probability that a randomly selected person or randomly selected dot is not using internet? So the probability of not using internet will be, we're gonna again relative frequency, right? How many people are not using internet? 220. And then here the denominator got to be the total number of people you ask. So it's going to be 1782 plus 220. All right. Now you see here, sometimes the this total is not given. They just list, give you how many people say yes, how many people say no. You have to add them up. So that is 220 divided by, you add this up, you get a 2002. So the answer is 0.110. When we write in decimal places, at least you should keep 3 decimals. Okay, so 1, 2, 3. Because if you want to change that into percentage, then it's going to be like 11.0%. Okay, either way. So that's your answer. All right. Now, when we say the chance, if the chance, remember 0.05 is a magic number in statistics. Magic number 0.05. Okay. If this number is greater than 0.05, then what are you going to say? We're going to say it's not significant, right? If the chance is less than 0.05, we're going to say it is significant. So this is our magic number. Okay. All right, now a couple of more things. One, remember the probability of A is always greater than or equal to 0, less than or equal to 1. Okay? And the probability of an impossible event, that will be 0, and the probability of certain to occur, that is 1. Okay, just quickly, just one more thing I want to let you know is P of A bar. All right, A bar means not A. Okay, and that is called complementary events. Okay, so I think that's everything you need to know for the basic concepts of a probability.